Have you ever been on a plane, maybe looked out the window at that massive engine hanging off the wing, and just thought about the absolute chaos happening inside? We're talking about a controlled, continuous explosion, an inferno, really, that's propelling this huge metal tube through the sky. So let's break this down, because when you look at the numbers, it seems completely impossible. Okay, so here's the heart of the problem. Inside that engine, the gas is burning at around 1800 degrees Celsius. But the super special metal alloys that make up the turbine blades, the parts that actually have to spin in that fire and harness all that energy, they start to melt at about 1400 degrees. So you've got a 400-degree problem where the inside of your engine is way hotter than the melting point of the engine itself. And just to give you an idea of how hot that is, 1800 degrees is way, way hotter than most lava flows. We're literally containing something more intense than a volcano inside a metal tube flying along at 35,000 feet. Which brings us to the big question, right? How is this possible? Why doesn't the core of the engine just liquefy and, fall apart moments after takeoff? Well, the answer is this brilliant 3-layer defense system that's honestly one of the coolest feats of modern engineering. So the first line of defense isn't some clever trick. It's the actual nature of the metal itself. You can't just use any old high-strength alloy for this job. Oh no. Engineers had to basically reinvent the material from the atoms up. This quote probably sounds a little weird, right? You don't grow metal. You cast it, you forge it. But in this case, growing is the perfect word, and it's the absolute key to their incredible strength. See, a normal piece of metal is made of tons of tiny little crystals or grains all jumbled together. The lines where these grains meet, those are weak points. Think of it kind of like old, worn-out Velcro. It holds, but you can peel it apart pretty easily. Under all that heat and force, those boundaries let the metal stretch and deform over time in a process called creep. But a single crystal blade, it has no grain boundaries, none. It's one continuous, perfectly aligned structure, like a brand new strip of industrial-strength Velcro. There's just nothing to peel apart. It's fundamentally stronger. And this is what you get. These aren't just sculpted hunks of metal, they are man-made crystals, each one grown oh so carefully from a single seed to create a flawless internal structure. It's just beautiful engineering. And the payoff for all that work? Get this, that single crystal structure gives the blade up to 9 times the resistance to that creep and heat fatigue compared to a normal cast part. 9 times. That's a huge leap in material science. But even this incredible supermetal isn't enough by itself. Okay, so the material itself is a masterpiece, a true supermetal. But it's still metal. And at 1800 degrees, even this perfect crystal is going to have a bad day. So engineers needed a second layer of defense, a way to make sure the worst of that heat never even gets to the blade in the first place. You know the best way to picture this? Think of that dessert, the baked Alaska. You've got ice cream, right? And it goes into a hot oven, but it doesn't melt. How? Because it's protected by that fluffy, insulating layer of meringue. Well, the jet engine does almost the exact same thing. This right here is the engine's meringue. It's called a thermal barrier coating, or TBC. It's this incredibly advanced ceramic that's sprayed onto the blade in a layer that's only about as thick as a few human hairs. This ceramic is a terrible conductor of heat, which is exactly what you want. It creates this barrier, keeping the metal underneath hundreds of degrees cooler than the scorching gas flowing just millimeters away. And applying it is a whole process. First, you've got your single crystal blade. Then they put on a metallic bond coat, which acts like a glue and also fights off rust. And then, finally, the ceramic top coat, the real heat shield, gets sprayed on top of that. All right, a super metal core, a ceramic heat shield, 2 layers down. You'd think that'd be enough, right? Nope. For maximum safety and performance, engineers added a third, and honestly, the most ingenious defense of all. They decided to use the engine's own air against the heat. This is where things get really clever. So the engine actually siphons off a huge amount of air from the compressor section. This is after the air has been squeezed and heated up, but crucially, before it gets mixed with fuel and set on fire. This air then gets rerouted away from the main event in the combustion chamber. Now, when I say cooler, that is a very, very relative term here. This air is still a blistering 700 degrees Celsius. But hey, compared to the 1800-degree inferno raging just outside, it's practically an ice bath. This 700-degree air is forced through a complex network of tiny, winding passages inside the hollow turbine blade. This whole technique is called film cooling. The air rushes through this maze inside the blade, cooling it from the inside out. And then it exits through thousands of tiny holes that have been drilled by lasers all over the blade's surface. This makes the blade sweat a protective cushion of cooler air all over its own skin. So that superheated gas from the combustor, it just flows right over this film of air, never actually making direct contact with the blade at all. It's amazing. But here's the trade-off. A staggering 20 to 30% of all the air the engine compresses isn't used for combustion and thrust. Nope, it's used just for this cooling system. That's a huge hit to efficiency, but it's the price you have to pay to run an engine so far beyond the normal limits of its own materials. So there you have it, the whole system. It's not one single solution, but three incredible technologies all working together. You've got the core, made of a grown single crystal superalloy for strength. You've got the shield, a ceramic coating to block the heat, and you've got the cushion, a film of cool air to keep that inferno from ever touching the metal. But of course, the push for better, more efficient engines never stops. And in this world, that means pushing temperatures even higher. So what's next? Well, engineers are already working on the next generation of materials. Say hello to ceramic matrix composites, or CMCs. These materials are a total game changer. They can handle even higher temperatures than our best superalloys. They weigh only a third as much. And this is the really important part. They need way less cooling air. And why does that matter? Well, less air for cooling means more air for thrust. And that translates directly into engines that are way more fuel efficient, which is exactly what we need for the next generation of air travel. So the next time you're on a flight, just remember this incredible high-stakes balancing act that's happening just a few feet away from you. It's this elegant dance of material science, thermodynamics, and pure cleverness, all just to overcome one fundamental problem, the melting point of metal. It really makes you wonder, doesn't it? What other impossible feats of engineering are we just taking for granted every single day?